Hi dears, today we can discuss the topic the decay of charge in a series LCR circuit. We have already discussed the growth of charge in a series LCR circuit yesterday. Now look at this figure and consider a circuit containing a capacitor, an inductance and a resistance which are joined in series with an applied EMF E. Here the key K2 is kept open. Then the capacitor is charged to the maximum charge Q0 by closing the key K1. Now we can open the key K1 and close the key K2. Then there will be no applied EMF across the capacitor. Then the capacitor starts to discharge through the inductance and the resistance. Now let I be the current in the circuit and Q be the charge in the capacitor. Then we know the circuit equation will be L di by dt plus IR plus Q by C will be equal to 0. And we have I is equal to dQ by dt and di by dt is equal to d square Q by dt square. By substituting this, L d square Q by dt square plus R dQ by dt plus Q by C is equal to 0. Now, I am going to rearrange this equation by dividing with respect to L d square Q by dt square plus R by L dQ by dt plus Q by LC is equal to 0. Now, to solve this equation, to get the instantaneous expression, as in the previous case, I am going to substitute R by L is equal to 2B and 1 by LC is equal to K square. That is equation number 2. Then let us substitute 2 in 1, which gives d square Q by dt square plus 2B dQ by dt plus K square Q is equal to 0. Now, as in the previous case, we can substitute Q is equal to X d square x by dt square plus 2b dx by dt plus k square x equal to 0. And we have the solution of such an equation as a e raised to alpha t. Then by substituting for d square x by dt square and dx by dt, we can write it as alpha square plus 2b alpha plus k square, for which we have the solution as minus b plus or minus root of b square minus k square. That is, we can write it as Q is equal to e raised to minus of b plus o root of b square minus k square into t plus b minus e raised to minus b minus root of b square minus k square into t, which will be given as equation number 3. Here, where a and b are some arbitrary constant. Now we can find out the a and b from this figure. When t is equal to 0, q will be equal to q0. Then equation 3 implies simply this exponential term will be e raised to 0 and this also will be e raised to 0. So we get q is equal to q0 at t equal to 0 plus is equal to a into 1 plus b into 1, which is simply a plus b is equal to q0. That is equation number 4. Now the next condition t is equal to 0, dq by dt is also equal to 0. Then dq by dt is equal to a into minus of b plus root of b square minus k square e raised to minus b plus root of b square minus k square into t plus b into minus b minus root of b square minus k square e raised to minus b minus root of b square minus k square into t. Then we substitute this condition, t is equal to 0, dq by dt is also equal to 0. That implies dq by dt LHS is equal to 0 and the exponential terms also will be 1. Remaining a is equal to minus b plus root of b square minus k square plus b into minus b minus root of b square minus k square. That is minus b into a plus b plus root of b square minus k square into a minus of b equal to 0. Now we have from equation 4 a plus b is equal to q0. So we can substitute here minus b q0 plus root of b square minus k square into a minus b will be equal to 0. By rearranging, a minus b is equal to bq0 by root of b square minus k square. Substitute it as equation number 5. Now, by adding and subtracting these two equations, we can obtain the solution for A and B. That is, by adding 5 and 4, we get 2A is equal to q0 plus bq0 by root of b square minus k square. From this, A will be q0 by 2 into 1 plus b by root of b square minus k square. And similarly, when we subtract equation 5 and 4, we get b is equal to q0 by 2, 1 minus b by root of b square minus k square. Now, we got the solution for the arbitrary constants A and B. Now, let us substitute this in equation number 3, which is representing q. That is, q is equal to, in place of A, we can write q0 by 2 into 1 plus b by root of b square minus k square into e raised to this term, plus q0 by 2 into 1 minus b by root of b square minus k square into exponential. That is, q is equal to q0 by 2 into e raised to minus bt into 1 plus b by root of b square minus k square into e raised to root of b square minus k square into t plus this term. In that, we have taken outside e raised to minus bt from this and e raised to minus bt from this as a common, and we have q0 by 2 into e raised to minus bt inside the bracket, these two terms. Then, this expression for q is known as the instantaneous expression for the decay of charge in a series circuit having an inductance, capacitance and a resistance. Now, we have the solution for instantaneous expression as q is equal to q0 by 2 e raised to minus bt into this term. Now we can find out the three special cases where b square is greater than k square, b square is equal to k square, and similarly b square is less than k square. When b square is greater than k square, root of b square minus k square is real or positive. From this, the charge of capacitor decays exponentially as e raised to minus kt becomes 0 fast. That is, the oscillatory function in this equation is overdamped by the real exponential function as b square is greater than k square. So, this condition is known as overdamped or deadbeat. In the figure, when we represent the charge along y-axis and the time along x-axis, and if this is q0, we can draw the overdamped condition like this. It is decreasing or discharging exponentially. Now we can go through the second condition, b square is equal to k square. That is, q is equal to q0 e raised to minus bt. We get, while substituting b square is equal to k square in this equation as we have got from the previous case of growth. Here it is a perfect exponential term. There is no oscillatory discharge. So, the charge decreases to 0 exponentially in a short time than before. And this is known as critically damped condition. We can draw this like this. That is critically damped. Then next one, the case 3. That is, in this, when we apply to the solution, root of b square minus k square is imaginary. So, we can substitute it as root of b square minus k square is equal to I omega. That is, omega is equal to root of k square minus b square. So, while substituting this, we get q0 by 2 e raised to minus bt into 1 plus b by I omega e raised to I omega t plus 1 minus b by I omega e raised to minus I omega t. Now, we can rearrange it as q0 e raised to minus bt, and I am going to substitute 2 to separately these two terms. Before that, this term will be e raised to I omega t and this will be e raised to minus I omega t. We can write together e raised to I omega t plus e raised to minus I omega t by 2 plus b by omega into e raised to I omega t minus e raised to minus I omega t divided by 2i. That is q0 e raised to minus bt into cos omega t plus b by omega sin omega t, where we know e raised to I theta plus e raised to minus I theta by 2 is equal to cos theta, and e raised to I theta minus e raised to minus I theta by 2i is equal to sin theta. So q is equal to q0 e raised to minus bt into cos omega t plus b by omega sin omega t. Now we know omega is equal to root of k square minus b square. From this, omega square plus b square is equal to k square. That is, we can draw it like a figure like this, where k is a hypotenuse and b and omega are two sides. Theta is the angle between k and omega. From where we can write b by omega is equal to tan theta. And also 1 by cos theta will be here k by omega, or cos theta is equal to omega by k. So we can substitute here q0 e raised to minus bt into cos omega t sin theta by cos theta sin omega t. q0 e raised minus bt divided by cos theta into cos theta cos omega t plus sin theta sin omega t after taking LCM. So by substituting b by omega as tan theta, we got this. Now I am going to substitute 1 by cos theta as k by omega. That is q0 e raised minus bt k by omega cos omega t minus theta, where cos a cos b plus sin a sin b is cos omega t minus theta, or it can be written as sin omega t plus theta. Here, look at this equation. We have an exponential damping case and also an oscillatory term. So, it is a damped oscillatory. Together, there is an exponential damped oscillation exponentially damping, and also there is an oscillation towards q0. Now, we can represent this graphically, and this condition is said to be damped oscillatory. And this is the graphical representation for the three conditions: overdamped, critically damped and damped oscillatory. In damped oscillatory, the charge oscillates above and below the zero as it finally settles down to zero value. Here, the charge decays exponentially to zero, then oscillates about the minimum. But the oscillations are damped due to the presence of e raised to minus bt term. And this condition is said to be damped oscillatory. Now, we can just go through the importance of an oscillatory circuit. We have to study the electrical oscillation in a circuit having inductance, capacitance and a resistance. So, when the capacitor is charged, the energy 1 by 2 CV square is stored in the electric field of the capacitor. When it is discharged, the magnetic field is set up around the inductance, and now the energy is stored in the form of magnetic field. Now there are two cases. If the resistance of inductor is high, the energy is lost as heat. If the resistance of inductor is negligibly small, the magnetic field recharges the capacitor, or the magnetic energy recharges the capacitor. Now, due to this recharging of the capacitor, again the energy is stored in the electric field of the capacitor. If the process is repeated in the LC circuit having negligible ohmic resistance, there occurs the charge is stored, or the energy is stored in the electric field once, and then the energy is stored in the magnetic field, then again in the electric field, then magnetic field, etc. So, there is a to and fro motion of charges between the capacitor and inductor, which produces a variation in the electric and magnetic field, which leads to the production of electromagnetic waves. In such a way, there will be electrical oscillations in a circuit having inductance, capacitance and a resistance. Then, frequency of electromagnetic waves in such an LC circuit can be written as 1 by 2 pi LC. 1 by 2 pi root of LC. That's the importance of an oscillatory circuit. Thank you.